In contemporary cosmology, much of the way we describe the universe is expressed by 6 characteristics. What are they, and how can we utilize the electrogravity-magnetic principles of space-time engineering to describe them? Well, these 6 characteristics are the Hubble constant, the cosmic microwave background radiation temperature, the cosmological constant, the dark energy density parameter, the pressureless matter parameter and the deceleration parameter. In this episode, we shall derive the cosmological history of 2 of these parameters. The other 4 parameters were covered in the preceding episode. Let's begin. In order to save time and prevent duplication, we shall leverage off as much existing information as possible. We recommend that viewers review the 6 artifacts shown. The first artifact is a video presentation of the history of the cosmos, given at a conference organized by the Egyptian Center for Theoretical Physics, and hosted by CERN, in December 2022. The second and third artifacts are video presentations of the Hubble constant and cosmic microwave background radiation temperature, respectively. The fourth artifact denotes the scientific basis and content for the first artifact, whilst the fifth and sixth artifacts denote the mathematical derivation underpinning all scientific claims presented herein. Now may be a good time to pause this video presentation, and review the recommended artifacts. Please keep in mind that this video presentation is a companion document to the artifacts appearing on screen. Please also note that the derivation of the cosmological history of the Hubble constant has been outlined in a 4-step process, appearing as emphasized. If you would like to understand how these equations have been derived, you can read about it, or you can take the easy path and reach out to me for guidance. I'll be happy to help. With the recommended artifacts reviewed, we shall tackle the lowest hanging fruit first, on the next slide, by moving directly onto the cosmological history of the cosmic microwave background radiation temperature. Here we have the cosmological history of the cosmic microwave background radiation in the primordial universe. You will instantly recognize the black body radiation curve similarity. This was not intentional. Black body equations were never utilized in its derivation, but the fact that its shape mimics a black body curve is very comforting. The illustration contains 4 graphs. The first graph is the cosmic microwave background radiation in the time domain. Note that the temperature of the universe at the instant of the Big Bang was 0 Kelvin, so, the Big Bang was cold. The cold Big Bang model was abandoned by physicists after the WMAP and Planck satellites observed the cosmic microwave background radiation which we see today. However, in our solution, the cold Big Bang hides behind a hot Big Bang observation. In other words, the universe was 0 Kelvin at the instant of the Big Bang, but rose to 10 to the power of 31 Kelvin, within the first 10 to the power of minus 42 seconds, so in fact, the WMAP and Planck satellites are blind to cold Big Bang evidence. Hence, cold Big Bang models cannot be excluded from the standard model of cosmology. This is an important takeaway. The other graphs are the first time derivative, second time derivative, and third time derivative. Thus, with the graphs and equations shown, we have completely described the cosmological history of the cosmic microwave background radiation temperature. The standard model of cosmology conceptualization of the universe appears on screen. It's intuitive, simple and very easy to comprehend, however, it is profoundly limiting. A significant problem with this representation is that it does not visually communicate any aspect, or even the existence, of the quantum vacuum, let alone the quantum vacuum ground state, that is, the zero-point field. The standard model of cosmology representation of the universe is derived from general relativity. Unfortunately, the future of cosmology is not general relativity. The future of cosmology is the quantum vacuum, that is, the integration of general relativity with quantum mechanics. The most obvious integration point between these two disciplines is the quantum vacuum. It is important to note that, in the standard model of cosmology conceptualization shown, the diameter of the sphere denotes the size of the observable universe, that is, approximately 92 to 93 billion light-years. Illustrated on the right-hand side of the screen, is the quantum model of cosmology. The quantum model of cosmology is an equivalent representation of the standard model of cosmology, but also includes the quantum vacuum. The quantum model of cosmology is a sphere of Hubble radius, enveloping the quantum vacuum. Specifically, the quantum vacuum in its ground state, termed the zero-point field. The radius of the sphere changes with Hubble time, and the observable universe rests upon the surface of the sphere. This means that, in order to circumnavigate the observable universe, a traveler must move all the way around the sphere, returning to their starting position. By doing so, the traveler has moved approximately 92 to 93 billion light-years, which is equal to the diameter of the standard model of cosmology conceptualization on the left-hand side of the screen. In other words, the perimeter of the quantum model of cosmology equals the diameter of the standard model of cosmology. We exploit this relationship in order to derive some astonishing experimentally verified results, thus proving that the true age of the universe is the Hubble age. An important aspect of cosmology which has not been adequately addressed by the scientific community is the relationship between the zero-point field, also termed the quantum vacuum, and the 4D spacetime of general relativity. In this illustration, we develop two representations of spacetime. One of these is termed Hubble, the other is termed observational. Hubble spacetime is a sphere of Hubble radius, such that the Big Bang occurred at its center. However, equally importantly, the zero-point field in this illustration is also located at the center, expanding at the rate of the Hubble constant, h⁵. The physical properties of the zero-point field is a topic of discussion in its own right, so we won't be dealing with them in this presentation. In Hubble space-time, our physical universe exists on the perimeter of the circle, with the observational radius indicated by the semicircular arc, a²b, which is approximately 46 billion light-years. Consequently, the observable universe is represented by the complete length of the perimeter of the circle from A to A, which is approximately 92 billion light-years. You can see from the magenta box that Hubble spacetime and observational spacetime are geometrically synchronized. So, what is the relationship between these two illustrations? The relationship is that Hubble spacetime is an extra-dimensional representation of cosmological expansion, adjunct to observational spacetime. In recent years it has become clear, from increasingly accurate measurements, that the Hubble parameter obtained from cosmic distance ladder techniques is significantly higher than the values obtained by fitting the power spectra of temperature fluctuations in the cosmic microwave background radiation. This difference has been termed the Hubble tension. The Hubble tension is represented within these illustrations. Depicted inside the Hubble space-time sphere, we see the Hubble constant relating to the power spectra from the cosmic microwave background radiation and term this the cosmological Hubble constant, appearing as h⁵. Similarly, depicted within the observational space-time sphere, we see the Hubble constant relating to the cosmic distance ladder and term this the astronomical Hubble constant, appearing as h⁵. What are the resultant implications for merging the white sphere with the gold sphere? In other words, what is the outcome of merging the zero-point field with general relativity? 5D spacetime. Let's now look at the cosmological history of the power spectrum Hubble constant, that is, the cosmological Hubble constant. Here we have the cosmological history of the Hubble constant in the primordial universe. I realize that this illustration appears baroque, but once you get your head around some basics, it's not too difficult to follow. This illustration contains 3 graphs. It is important to note that all required equations appear on the illustration, so everything you need to replicate this solution is right in front of you. Everything you see here has been forwardly derived from first principles and nothing has been doctored, modified or fine-tuned. The first graph is the magnitude of the Hubble constant. The second graph is dH/dt, which is the rate of change of the Hubble constant in the time domain. The third graph depicts cosmological inflation and expansion. The next important feature to recognize is that each graph contains regions. Each region defines a specific phase of the evolutionary process. Region A denotes the period we term Planck inflation. This runs from t = 0 to T alpha, which is the instant of the Big Bang. I will also point out that the cosmic microwave background radiation was 0 Kelvin at the instant of the Big Bang. So, the Big Bang was in fact cold, but thermally inflated extremely quickly. Therefore, experimental observations of a hot Big Bang are blind to cold Big Bang evidence. Region B denotes the period we term thermal inflation. This runs from T-alpha to T1. At T1, the cosmic microwave background radiation reached its maximum value, which was approximately 10 to the power of 31 Kelvin. Region C denotes the period we term Hubble inflation. This runs from T1 to T2. From the graph you can see that the Hubble constant reduced to 0 by T1 for an instant, but immediately shot upwards again to its maximum post-T1 value, at T2. Its value at T2 was approximately 10 to the power of 60 km per second per megaparsec. Region D denotes the period we term Hubble expansion. This runs from T2 to the present epoch. Region E denotes the period of cosmological inflation, from T equals 0 to 2T phi rho. So, cosmological inflation ended when the universe was approximately 10 to the power of minus 23 seconds old. Region F denotes the broader period of cosmological expansion, from the Big Bang at T alpha, to the present epoch. An important takeaway from this illustration is that cosmological inflation was a multi-event, multi-process period. This is why we term it as being the cosmic envelope. Thus, with the graphs and equations shown, we have completely described the cosmological history of the power spectrum Hubble constant, that is, the cosmological Hubble constant. Let's now look at a present epoch summary of electrogravity-magnetic construct achievements. What you're seeing now is a comparative overview of key present epoch cosmological metrics. As you can see quite clearly, even at a quick glance, the correlation between solutions is astonishing. With one notable exception, cosmological age. Many of these results were published in the Hindawi journal, Advances in Astronomy in 2020. A couple of years ahead of the James Webb Space Telescope. I should also point out that our solution improves approximately 23% of the Particle Data Group 2022 Astrophysical Constants reference table. Appearing in the left-hand column we see the cosmic microwave background radiation constrained solution, and the standard model of cosmology solution in the right-hand column, which is cosmic microwave background radiation unconstrained. All derivations, proofs and applications of the electrogravity-magnetic construct are freely available online, or you can reach out to us directly and we'll be happy to help. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.